Hi grade 12s, we're going to be working through question 8 from the November 2018 chemistry paper. You can find all the exam question papers on EC exams. Please make sure that you have table 4B ready before we start with the questions. I'm going to read question 8.1. Corrosion is a redox reaction that takes place in the presence of oxygen and water. Rusting is the corrosion of iron leading to the formation of iron 3 ions. 8.1. Define oxidation in terms of electron transfer. Oxidation is the loss of electrons. That is the definition. Please learn it well. A cleaned copper rod and a cleaned iron nail are placed in a beaker containing water at 25 degrees as shown below. So they have the sketch there for you. After a while, it was observed that the iron nail was coated with rust. The copper rod showed no visible signs of corrosion. 8.1.2. Write down the half reaction for the iron nail. So if the iron nail forms iron 3 plus ions, so this is the half reaction. As it occurs on the table, it occurs as a reduction reaction with a reversible arrow. You need to swap that reaction around, because on the table the iron, the Fe, is on the right hand side. You need to have it on the left hand side. So it is an oxidation half reaction. So you just swap the half reaction around and remember to use a single arrow. Remember the little minus at the electron sign. So when they say that rusting is the corrosion of iron leading to the formation of iron 3 ions, please remember that they are giving you the charge here. Iron 3 ions are actually Fe3 plus ions. So that is how I know that this is the half reaction and it's not the half reaction with iron forming iron Fe2 plus ions. The black reaction is the reaction that is on table 4B. I just wanted to point this out to you, that the iron nail is the reactant. So it needs to be on the left-hand side. So we swap this around, so the reversible reaction is what is actually happening here. So therefore that is your answer. As I said before, please remember single arrows. Question 8.1.3. Does iron act as a reducing agent or an oxidizing agent in the beaker? It acts as a reducing agent. That is your answer. The black part is the explanation that I'm going to give you. The iron is oxidized if you look at 8.1.2's answer. Therefore, it is the reducing agent. The substance that is oxidized is the reducing agent. Question 8.1.4. Explain the above observation by referring to the table of standard reduction potentials. The table they're referring to is table 4. Most of your schools use table 4B, so I will only be referring to table 4B. The observation that they want you to explain is the fact that the iron rusts and turns to iron 3 plus ions, and nothing happens to the copper. So the first thing you must do is find these two half reactions on the table. I have marked them with a purple pen. So here's your Fe3 plus taking up 3 electrons forming iron, and here's the copper 2 plus taking up 2 electrons forming copper metal. Now remember, both of these reactions are reversible. We looked at the iron half reaction in the reverse as it was in question 8.1.2. So you always need to refer to these arrows on the right hand side and on the left hand side. On the right hand side I have just rewritten what it says: increasing, reducing ability as you go up the table, and that is referring to all these substances on the right hand side. On the left hand side, coming down, there's an arrow pointing down and it says increasing oxidizing ability. So you have strong oxidizing agents lower down, weak oxidizing agents higher up. On the right hand side are your reducing agents. So your strong reducing agents are higher up and your weak reducing agents are lower down. So I've indicated that there because we are only looking at part of the table. So if we look at the right hand side where our reducing ability is, which is what they are referring to, because in 8.1.3 we said that iron is acting as a reducing agent. So we only look at the right hand side. Iron is higher up, so it is a stronger reducing agent than copper. The answer Explain the above observation by referring to the table of standard reduction potential. So your answer is iron is a stronger reducing agent than copper, and iron will therefore be oxidized to form iron 3+ ions. Or you could say copper is a weaker reducing agent than iron, therefore copper will not be oxidized to copper 2+. Here is the answer to 814 again. Iron is a stronger reducing agent than copper. It is higher up on the table. And iron will therefore be oxidized to iron 3+ ions. Or you can say copper is a weaker reducing agent than iron because it is lower down on the table. Therefore, copper will not be oxidized to copper ions. Question 815. First of all, I'm going to read the piece above the sketch. To prevent rusting of an underground pipe, it's an iron pipe, the pipe is connected to a metal Q that corrodes easily. So in your sketch you have the iron pipe and metal Q, and then they are connected with a wire. 815. You are given two metals, zinc and copper, to use as metal Q. Which metal would be more suitable? Give a reason for your answer. So if we look at all three metals that we have now, here's your iron pipe. You have to choose whether you're going to take zinc or copper for metal Q. Which one do you think will oxidize more easily? Zinc has a greater reducing ability, so zinc will be oxidized more easily. So zinc is what I would choose for metal Q. Your answer is zinc is a stronger reducing agent than iron. Remember, our pipe is iron, so we want something else that will oxidize more easily. So zinc is a stronger reducing agent than iron. Copper is a weaker reducing agent than iron, so copper won't react, then your iron pipe will corrode. So you would choose zinc. I'm going to repeat that. Zinc is a stronger reducing agent than iron, so therefore the zinc will undergo oxidation before iron. Here's the answer written down. Zinc is a stronger reducing agent than iron. Remember, iron is the pipe. Zinc will therefore undergo oxidation before iron. Question 8.2. A galvanic cell is constructed using iron and iron 3+ half cell and a copper 2+ half cell. 821. Write down the overall net cell reaction that takes place when the cell is functioning. So when you do a question like this, you must always find your two half reactions. Iron 3+ going to iron and copper 2+ going to copper. Remember that there are a few half reactions for the iron and a few half reactions for the copper. Make sure that you choose the correct two. They give you the ions, iron 3+ and copper 2+, so you should not have a problem with identifying the two half reactions. The first thing you do when you're using table 4b, the top reaction is the one that is going to reverse and become your oxidation half reaction. The bottom reaction is the one that is going to be your reduction half reaction. So I'm going to write down those two half reactions now. Then you balance the electrons and then you work out your net or overall reaction. Okay, so we have identified the two half reactions on the table. They occur exactly like this on the table. The iron half reaction is above the copper half reaction. You swap the top half reaction around to form your oxidation half reaction. So this becomes that. Everything that is on the right is now on the left, and everything that is on the left is now on the right. Single arrow. The reduction half reaction, you take it down exactly like that, but you write an arrow going from left to right only. So you swap the top half reaction around to form the oxidation half reaction. The bottom half reaction is your reduction half reaction. All we now need to do is balance the electrons. The electrons must be the same in each half reaction. We have 3 there, 2 there. So I'm going to multiply this half reaction by 2 to get 6. And I'm going to multiply this half reaction by 3 to get 6. Here are the two half reactions now, multiplied by 2 and multiplied by 3, so that you have 6 electrons in each. The blue reaction is your answer for the overall or net cell reaction. 2 iron atoms react with 3 copper ions to form 2 iron ions and 3 copper atoms. A quick tip, always check to make sure that the sum of the charges on the left-hand side of the arrow equal the sum of the charges on the right-hand side. For example, the charge on this iron atom, these 2 iron atoms, is 0. The total charge here is 3 times 2, it's positive 6. The total charge on the right-hand side is also positive 6, 2 times positive 3, and the charge here is 0. So we have a total charge of positive 6 on the left and a total charge of positive 6 on the right. This is a good tip to check that you haven't made any careless mistakes. For example, if you had multiplied with the incorrect numbers, you would have picked it up here. Or if you had written a 3 instead of a 2, or a 2 instead of a 3 over there, you would pick that up if you had checked your charges on both sides. 8.2.2, we're going to use the equation from the data sheet. You need to calculate the cell potential of this cell under standard conditions. So the half reaction at the cathode is your reduction half reaction, which is the copper half reaction. So the cell potential for that one is 0.34. The half reaction at the anode is your oxidation half reaction, which is the iron half reaction. That cell potential is negative 0.06. The two negatives become a positive, so your cell potential under standard conditions is 0.4 volts. Remember, your answer must always be positive for it to be a spontaneous reaction. Non-spontaneous means that you would have had to add electrical energy in the form of a cell or battery for this to take place. This happens without a cell or a battery.